You write down 12 words on paper. From those 12 words, your wallet generates billions of Bitcoin addresses. Lose your phone, and any compatible wallet regenerates every single one. If all those keys come from the same source, why doesn't breaking one break them all? To understand the magic, we start at the root. Your recovery phrase becomes a binary seed. That seed feeds into HMAC SHA-File12, a keyed hash function that produces 512 bits of output. The key input is the fixed string Bitcoin seed. The output splits cleanly in half. And the left 256 bits become your master private key called M. The right 256 bits become the master chain code called C. Multiply M by the generator point G on the elliptic curve, and you get the master public key M. Those three values, M, and C, are the root of the entire tree. The chain code deserves a closer look. It's extra entropy bundled alongside each key. Without it, derivation cannot happen. With it, you can generate children, but crucially, siblings remain computationally unrelated to each other. If you hold one child key but not the parent's chain code, you cannot compute that child's brothers and sisters. The chain code is the gate. It's what makes the tree deterministic yet compartmentalized. Remember this because it becomes the center of both a superpower and a vulnerability. Here's how child key derivation, or CKD, works. 3 inputs go in: the parent key, the parent chain code, and the 32-bit index choosing which child. They're concatenated and fed into HMAC SHA-512. The 512-bit output splits again. The left 256 bits get added to the parent private key, modulo the curve order n, producing the child private key. The right 256 bits become the child's own chain code. That child now has everything it needs to be a parent itself. Repeat the process at any depth, and you build a tree where every node is deterministically derived, yet siblings stay isolated from each other. A key plus its chain code is called an extended key. 2 flavors exist. The extended private key, xprv, holds the private key and the chain code together. With xprv, you can derive the entire private subtree below that node. The extended public key, xpub, holds only the public key and the chain code. With xpub, you can derive every public key in the subtree but no private keys. In base 58 check encoding, these start with the prefixes xprv and xpub, which is exactly how they got their names. This split unlocks a powerful deployment pattern. An e-commerce site needs a fresh Bitcoin address for every customer. Putting the private key on a web server is reckless. Instead, the company generates an xpub on an offline machine and copies only that xpub to the server. The server derives a new receive address for each checkout forever without ever touching a private key. The xprv lives on an air-gapped signing device that never connects to the internet. When funds need to move, transactions travel to the code device by USB, get signed, and come back out. This tree structure is powerful, but it has a subtle weakness. Here is the weakness. Suppose an attacker steals your xpub. By itself, that leak only exposes public keys, which is annoying but survivable. Now suppose one child private key also leaks, maybe from a careless signing setup. Watch what happens. The attacker reverses the CKD math. From the xpub, they recompute the left half of the HMAC output for that child's index. From the leaked child private key, they subtract that left half modulo n. What pops out is the parent private key, catastrophic reversal. Now holding the parent private key and the chain code, the attacker derives every sibling private key in the entire subtree. One leaked child plus the xpub equals total compromise of the branch and everything above the leaked key. This is why treating xpub as casually shareable is dangerous. The chain code, the thing that makes derivation work, is also the thing that lets an attacker walk the tree once a single private key escapes. Hardened derivation is the firewall that kills this attack. The fix is almost surgical. In normal derivation, the HMAC input uses the parent public key. In hardened derivation, swap it for the parent private key instead. The resulting chain code output can no longer be reverse engineered using only the xpub because the xpub doesn't know the private key. The cascade stops. A leaked child at a hardened level cannot expose its parent or its hardened siblings. The trade-off is explicit. At a hardened boundary, you lose the xpub superpower. You can no longer derive child public keys from the parent public key alone. You gain isolation. That's the deliberate trade. Convenience at the leaves, isolation at the top. How does the wallet know which mode to use? The 32-bit index, indices from 0 up to 2 to the 31st minus 1 mean normal derivation. Indices from 2 to the 31st up to 2 to the 32nd minus 1 mean hardened. The split is exactly in half. In hex, 0600000 marks the boundary. When you see the notation 0 apostrophe, that's hardened index 0, which really means 0600000. Some tools write it as 0h instead because shells interpret the apostrophe as a quote character and the mango paths. The apostrophe and the h are interchangeable notation for the same hardened flag. Now the standard BIP-44 path makes sense. Consider m/44, apostrophe/0, apostrophe/0, apostrophe/0/5. The top 3 levels are hardened: the purpose, the coin type, and the account. Those apostrophes isolate the master key from any account level leak. The bottom 2 levels, the change flag and the address index, stay normal. That's deliberate because it lets you export an account level xpub to a web server and generate unlimited receive addresses at the leaves without exposing anything above. Hardened at the top, normal at the bottom. Cold storage devices, watch-only wallets, exchange deposit infrastructure, hardware wallet standards, all of them depend on this single design choice. BIP-32 didn't just give us convenience from one seed, it gave us a complete security architecture.